Hello viewers and welcome back to my class. In this video we want to talk about real analysis, a topic that said finite set, enumerable set and countable set. Okay, but before we talk about these three things, there are things that we need you to know. The first, let's just have a revision on a review. Let us review one-to-one some types of functions. The first one is one-to-one function, and another name to one-to-one function is the injective. Okay, one-to-one or injective function. So another one we'll look at is an onto function, onto or surjective function. Surjective function. Then the last one that we'll look at is bijective function. Bijective function. Now, from the word bijective function, from the word bi, you will know that it means two. So a bijective function is a function that is one-to-one and equally onto. So if you have any function that is one-to-one and as well as onto, then that function is what? A bijective function. So let's start with the first one. Let's start with the first one, which is one-to-one function. One-to-one function. Okay? Now, given a set, given two sets, A and B, okay? Given two sets A and B, a function, let's say f, that maps A to B, okay? That maps A to B is called one-to-one or injective if and only if given x comma y that belong to that A, okay, we have that if x is not equal to y, okay, will imply that f of x will not be equal to what? F of y. Okay, so now this thing simply means that given two functions, given two sets A and B, and we have a function f that maps A to B, we say that this function f that maps A to B is one-to-one if and only if we can pick two elements in A. If we pick two distinct elements in A, their images have to be distinct. Okay, their images have to be distinct, or pick that two distinct points or two distinct elements must have two distinct images. What do I mean by that? Let me show you geometrically. If I have a function like this, example, if I have a function A, B, C, this is a function A like this, and then I have a function, this is a set A and set B like this, and I have 1, 2, 3 like this. That, for example, that this produces this produces this, and maybe this produces this. You will see that, okay, this function, this maps to this as f. You will see that f is one-to-one. Why? Because each element of the primitive, we call this primitive. Which element of the primitive, okay, if it's in a set, we call them the domain. Each element of the domain produces a unique element of the codomain or the range. Okay, so like nobody, I cannot say that maybe A and B produces just one person, then it is no longer one-to-one. Even from the name one-to-one, one person will produce just one thing. If we are not the same, we are not producing the same thing. If we are the same, then we produce the same thing. Okay, so this is an example to that. We are going to take more examples. This is an example to that. So if you are distinct, if A is not equal to B, and A and B are coming from here, they will not give you something that is equal. So that is distinct elements produces distinct images. As far as we are not equal, we will not produce the same thing. Are you getting that? So this is one example. Let me give you another example. Another example say that okay, let me write it here. Or let me write the contrapositive statement of this. The contrapositive statement of this say that equivalently, okay, let's have a function f that maps a to b. Okay, if we say that a function f maps a to b is 1 to 1, is 1 to 1, is 1 to 1, if and only if f, if and only if f x is equal to fy, okay, will imply that x is equal to y for all x and y, which is an element of a. Okay, so now this one is saying that as far as our images are equal, it means that we are equal. As far as we have the same images, that means we are the same point. So two equal points produces two images. So an example to that is that, for example, I have something like this. I have this is A, and A is X and X. Then I have B. Okay, sorry, I have B here, which is maybe anything here, maybe M. That's A, and if these two things producing the same thing, that means that they are equal. Or if I have that here is y, even if here is y, as far as the both of them producing the same thing, it must x must be equal to y. So for us to produce the same thing, we must be equal. So that is the contrapositive statement of this. So the two statements are equivalent. So it's either you show that, we can call this equation 1, equation 2. It's either you show that if we are distinct, then our images will be distinct. Or you show that if we produce the same thing, then we are equal. Once you can show these two things, then you are good to go. That means that that function is what? 1 to 1. Okay? Or injective. So let's give an example to that. This one is just for you to see what we are saying. An example. You can say consider the set n. Consider the set of natural number. I hope you know that natural numbers 1, 2, 3, 4 continues to infinity. Consider this set, and then another set E, for instance, another set E which is equal to let's say 2, 4, 6, 8, like that. A set of even numbers, okay? And defined by a function, we define a function f that maps this natural number to E by f of x is equal to, or rather f of n is equal to 2n. Okay? For all n belonging to the natural number. Okay. Now, let's consider this. It is obvious that this function is 1 to 1. But let us see if it is 1 to 1. Now, we are given, let's see if it is 1 to 1. We are given n1, okay? We are given n1 and n2 that belongs to this n. We are picking any two elements here. Okay? If we are picking any two elements here, and then we now say that n1 is not equal to n2. We are picking two distinct elements here. You will notice that if I put the n here, I'm going to have that it is obvious that 2 multiplied by that number will not be equal to 2 multiplied by the other number. It is obvious. Pick any two elements here and multiply it by 2. They will not be equal. If I pick 2 and 3, 2 times 3. Sorry. My daughter just obstructed this. Okay. Oh yeah, go. 1 minute. Okay, sorry about that. So I was saying that if I pick two elements from the natural number and I multiply that number by 2, they can never be the same. 2 times 2 is 4. 4 can never be the same thing as 2 times 3 is 6. So it is obvious. And 2n1 is the same thing as saying fn1, because 2n is the same thing as fn. So 2n1 is equal to 2fn1, and 2n2 should be equal to what? Fn2. Okay? So since they are not equal, these two must not be equal. You see that? So therefore, we conclude that what? If n1 is not equal to n2, it will imply that fn1 will not be equal to what? Fn2. So therefore, we say that f mapping n to what? Mapping natural number to what? E is what? 1-to-1 function. 1-to-1 function. Okay? So that is our first example. So let's look at the next example. Example number 2. So this one now, we use the first statement. So when two distinct elements are not, that two distinct elements must give you distinct images. So now, let us use the second example that says that if the images of two elements are equal, obviously that they are what? Equal. Okay? That their points are equal. So example 2, we have that given a set A which is equal to 0, 1, close and open interval, and we have a set B which is equal to a set of real number, then we now have that a function, then the function f that maps A to B, or that maps this to this, defined by for all x we pick in this A, okay, defined by for all x we pick in this A, that f of x, or defined by f of x, anyone, they are still the same thing, defined by f of x is equal to x over 1 minus x for all x we pick in A. Okay, now we want to show that this function is 1-to-1. That means if we pick two elements of A and their images are equal, then that means they are equal. So let us show that. Solution. So we say let x and y be an element of A. We are picking x and y from A. Okay. So if you are picking f and y from A, that means f of x will now be equal to x of 1 minus x. And f of y will now be equal to what? Y over 1 minus y. Now, if we assume that f of x is equal to f of y, then we now wish to show that x is equal to y. So now bring down this. So x over 1 minus x is equal to what? Y over 1 minus y. So if we cross multiply, we are going to have that x in bracket of 1 minus y is equal to y in bracket of 1 minus x. Okay, so we have that x minus what? Xy is equal to what? Y minus xy. So if I add xy to both sides, I'm going to be having, if I add xy to both sides, I'm going to be having x minus xy plus xy is equal to y minus xy plus xy. I'm adding xy to both sides. So this and this is gone. I am left with x is equal to this and this is gone. I have y. So this implies that if f of x is equal to, this implies that, or therefore, if f of x is equal to f of y, it implies that what? That x is equal to y. That x is equal to what? Y. Okay? So that is that, and very simple to show. So since we have this, what do we conclude? We conclude that the function f that maps A to B is a 1-to-1 function, or you call it what? It's an injective function. Okay? So now let's now talk about onto function. That is surjective function. Okay? Then we'll now talk about bijective function. Then we are done. Then in the next video, we now move to telling you about finite, countability, and denumerable sets. Okay, so now onto function. Onto function. Onto, or you call it what? Surjective function. Okay, so now a function f that maps A to B is called an onto function. It's called an onto function if and only if, okay, for any y that we pick in B, the codomain. Okay, for any y we pick in B, there exists x that depends on that y belonging to A, okay, belonging to A, such that f of that x that belong to A must give you y. So let me explain this, the meaning of this. Now this means that for every point in the codomain, for every point we pick here in the codomain, okay, for every point we pick in the codomain, we can find a point in the domain. We can find a point in this domain which x sends to y, okay, which x sends to y. That is to say that every element in B is an image of a particular element in A. Let me explain this very well. Like, any point we pick here is a result of somebody here. You understand? So another way to say this is that the codomain must be equal to range. That is, everybody in the codomain is useful. Let me give you an illustration. If I have something like this, look at this. If I have that this is A, B, and C, and then I have maybe, let's have something like this: 1, 2, 3, and 4. If I have that this is this, and this is this, for example, and then maybe this is this. Now I have that this is set A and set B, and then this function maps it. Now we cannot say that this is an onto function. Why? Because we can find an element in B that is not an image of an element of A. Do you understand what onto means now? Onto means that every element you pick in B must be an image of an element in A. So for example, now maybe we have that this one equally produce somebody here. Maybe we have something like this. Then we can say that this is onto. In fact, the shortcut for onto is that the codomain must be equal to range. Okay, that is, everybody on this side is useful, is a product of somebody. In fact, we don't want to waste anything. As far as you are a product, somebody produced you. That's the meaning. Okay, so know that onto simply means that the codomain must be equal to range. That is, everybody on the codomain is useful. Okay, so this is a typical illustration of that. This will help you to understand it very well. So let us take an example. So this is said that what? That a function f that maps A to B is called an onto function if and only if we can find an element y in the codomain, okay, if we can find or any element we find in an O domain, for any element we find in an O domain, there exists an element here, okay, such that element is an image of this. Are you getting me? So that element is an image of that y. So I don't know, from this will help you to understand it better. So an example to that. Example. So example. So we have that. Let's see an example. Okay. Given the function f, okay, or given two sets. Let's use the first example we used in the other one. Let's use that same example. Okay. Consider n, which is equal to a set of 1, 2, 3, 4, a set of natural number, and e which is a set of 2, 4, 6, 8, dot, dot, dot. Okay? Consider these two sets, and F maps A to B, and F maps N to E, okay, by F of X is equal, F of N. F of N is equal to 2N for all N belonging to what? To a natural number. Okay? Now, if we have this, we will conclude that what? That this function F is 1 to 1. Why? Because before we prove that, you will notice that any element you pick here is an image of somebody here. It's a must. In fact, any element you pick here can be given as, pick any element, that element must be given as 2 multiplied by a number, and that number must be coming from here. Pick 2, for example. 2 can be written as what? 2 times 1, and 1 is here. Pick 4. 4 can be written as what? 2 times 2, and that 2 is here. All these people are the N that belongs to this natural number. So there is nobody that you will pick here that is not an image of somebody here. It's not possible. So that is why we say that what? That this function is what? Onto. But let us show that. Let us just show that. Okay. Let us just show that. Solution. Okay. Solution. We have that where is it? Okay. Solution. We have that for all y that belongs to E, for any element we pick in E, okay, there exists, this implies that there exists, let's say n, okay, we have used n here. There exists, what am I saying? Okay, there exists n that depends on y, or let me use m. There exists m that depend on y, okay, that is an element of a natural number. If we can find any element, for any element we find here, okay, there exists an element here that belongs in this one, okay, such that 2 times that element you find must give you that y. Okay, 2 times that will give you that y. Hence we say that F is a surjective or and what? Onto function. As simple as that. In fact, before I started writing this, I've already explained it. Any element you pick here is an image of somebody here. It's a must. It's a must. So anybody you pick here, you can find somebody here that you can write as 2 times that same person. You understand? So that is that. So let's give one more example on this, and then think we are good to go. So another example. Example 2. Example 2 said a function f maps 0, 1 to 0, positive infinity. Okay, the function this maps this to this. Then they now say given any x that belongs to this 0, 1, okay, by, let me write this very well. Let me write it as given set A, which is equal to 0, 1, like this, and set B, which is equal to 0, positive infinity. Okay, a function a function f that maps A to B, okay, given denoted by f of x to be equal to x over 1 minus x for all x that belongs to A, okay? Now, given this function, we will say that this function is an onto function. How? This function is an onto function. How? Is because for any element you pick here, okay, is an image of an element you pick here. Pick 0, for example. If you pick 0, 0 over 1 minus 0. What do we have? 0 divided by 1 minus 0 is 0 over 1. And 0 over 1 is 1. 1 is found here. Pick another element. If I pick half over 1 minus half is half over half. And half over half is 1, is here. So there is no element you will pick here and then substitute here that will not give you somebody here. Or anybody you, in fact, get anybody from here, self. Get anybody from here. From 0 to, in fact, get 5. Anybody you get here, if you equate it to this person, you can easily find x that belongs here. Let me give you an example. Give me any number here. Let's say 5. If we say that 5 is equal to x over 1 minus x, cross multiply, we have the what? 5 into 1 minus x is equal to what? Is equal to x. So what do we have? Make s subject to have that 5 minus 5x is equal to x. So we have that 5 is equal to what? X plus 5x. So we have that 5 is equal to what? 6x. So x is equal to what? 5 over 6. 5 over 6 falls between 0 and 1. So any element you pick here is an image of somebody here. So that is what? An onto function. But let us solve it to prove. I'm just showing you an example. Okay? Let us solve it to prove that. Solution. Now, let us get solution. Okay. Let us get our y. Let's say let y be equal to, from what I did, I'm picking an element here. Let's pick an element here, y, which is equal to, you equate it here to find your x, which is equal to x over 1 minus x. If I cross multiply, I'm going to have that y in bracket of 1 minus x is equal to x. So therefore, y minus xy is equal to x. So therefore, y is equal to x plus xy. So therefore, y is equal to what? X in bracket of 1 plus y. So x staying alone, I have what? Y over 1 plus y. Okay? So with this now, we are going to say that, we observe that for any y that I pick here, for any y that I pick in B, there exists uy, let me call it u of y, or let me call it n of y, I like n of y, okay, which is equal to, we have gotten it. When I equated it to y, I got it, which is equal to what? Y over 1 plus y, okay? That belongs, we must get this, that belongs to set A. That belongs to set A such that f of that ny, okay, must be equal to y. Yes. If you put that function here, inside here, it must give you y. Let us check if it is true. So we know that f of x is equal to what? X over 1 minus x. So f of ny must give me what? Ny over 1 minus ny, right? But don't forget that we say that ny is equal to this. So if ny is equal to that, we are going to have that f of ny will now be equal to, ny gave us y over 1 plus y divided by 1 minus ny again. That is 1 minus y over 1 plus y. So if you do this, you are going to have y over 1 plus y divided by, the LCM here is 1 plus y. So I have 1 plus y minus y. Okay? So I'm having that y over 1 plus y divided by, what I'm having here is 1 over 1 plus y. So change divide to times. I'm going to have y over 1 plus y times 1 plus y over 1. So if this take care of it, see that I'm having that f of ny is giving me what? Y. Proved. You see? So we say that for any y we pick in B, there exists n of y which we got as this, which is an element of here, such that f of that ny must give you y. So you see that this gave us this. So we now conclude that what? Therefore, f is a surjective function or an onto function. An onto function. Okay? An onto function. So I'm going to give the last example to this particular concept, and then think I'm going to end there because I don't want my videos to be too long. Okay, so the last example, and this last example say consider the set, or consider the function f of r mapping to r from r to r defined by f of x, which is equal to exponential x for any x belonging to r. Okay, so now this function is 1 to 1. This function is 1 to 1, obviously. Why? Because pick any element here and put it in this function, or pick two elements here that are not equal, put it in this function. You must definitely, in fact, if x is not equal to y, therefore f of x, which is equal to exponential x, will never be equal to f of y, which is equal to what? Exponential y. It's not possible. Check it out. Okay, even if you draw the graph, this is your r to r, this is r to r. Okay, the graph will look like this, exponential. It will move like this to be parallel. From being parallel, it will move up to infinity. So this is the graph of f of x, which is equal to exponential x. You will notice that for any horizontal line I draw, that horizontal line must cut the function at most 1 point. It will cut the function it will not cut it more than 1 point. So that means for any value I pick on x, I'm going to have just one single value on y. So that means if two distinct elements of x will give you two distinct images. Are you getting me? So that is that. So in conclusion, geometrically, if a function is 1 to 1, geometrically, a function is 1 to 1 if it cuts the horizontal line at most 1 point. Please take note of that. Write it down. Note that geometrically, a function is said to be 1 to 1 if it cuts the horizontal line at least 1 point. And if you check that the function here, this is drawn like this, and it's going to cut the vertical line at 1, because exponential 0 is 1. So when x is 0, it's going to give us 1. So it's going to cut it at just 1. So any horizontal line you draw is going to cut it at most 1 line. If you draw it up, it will cut it at 1 line. If you draw it up, it will not even cut it at all. So that is when we conclude that this function f of x is 1 to 1. So thank you very much for watching. Please don't forget to like our video, share to your friends, and then if you are new to this channel, please subscribe. May the peace of the Lord be with you. Bye-bye.